Hello students, welcome to our final discussion on topic of gradually varied flow where we are qualitatively trying to develop various transition profiles, that is when channel changes its slope from mild to milder or milder to mild, mild to steeper. In previous sections, we learned about qualitative assessments of water surface profiles whenever flowing water encounters certain obstructions. For example, there could be a sluice gate or there could be a dam. So this concept would add more clarity that why do we really need to worry about these slope transitions and how they are applicable in real world. Now, let us say that we have a channel section which was having a mild slope, and after traveling certain distance, it is going to get translated into a milder slope. That is, there is a change from mild to milder as the water is flowing. Now, we know that in case of channel flow, our critical depth YC is independent of the slope because our yc is simply q square upon g raised to power 1 by 3. So does not matter whether our slope is milder or mild, our yc or critical depth of flow is going to be same. Now we also learned that by definition we say that a slope is a mild slope or anything related to m if critical depth yc is less than normal depth of flow. That would mean for a mild slope, our yn is definitely going to be higher than yc. And if our slope is even milder than a mild slope, our normal depth would keep on increasing because the asymptotic limit or upper limit is that when this slope becomes horizontal, our normal depth would tend to infinity. So that would help us remember that if our slope becomes less and less steeper, we are ultimately tending towards much larger normal depths. Now, if that is the case, water would be flowing when in a uniform flow at the depth equivalent to yn. But as it passes this section downstream of this milder slope, it would want to flow at the normal depth corresponding to this milder slope. Now the question is that it was flowing here and now it is going here. How this transition should take place? Or if we are trying to understand whether a gradually varying flow is possible or this transition has to be of some form of rapidly varying flow. That is the question that we are trying to answer here. So what we will do is that we will try to see all the possible pictures that ultimately it has to go here. What are the possible paths it can take? One way is that let us say that this is our cutoff point. Wherever this slope changes are happening, our water depth gradually start increasing here and it joins this as soon as it enters into the area after this threshold. This is which is here. It is entering this area at the depth of yn. Second option is it goes all the way till transition point, and from this transition point it starts its journey upwards because ultimately it has to reach here. And third option could be that is it goes here and it starts the upward journey somewhere before, but these are the three profiles that it could possibly take, and between these three profiles you can have as many cases, but ultimately we have to identify which one is the most plausible case. So let us try to understand why this profile is possible or not possible. Now, when we are talking about going along yn up to this point, there is no problem because this channel would be happy to maintain the flow depth equal to normal depth of flow for the mild slope. However, if you look in this region that I am now showing with this temporary highlight, we see that at this point, our depth of flow is between yn and yc. That means this is zone 2. And in zone 2, we only have receding profiles. If you recall, S2 as well as M2 both corresponds to case of drawdowns. They cannot be rising like this. They have to go down. That means this profile is not possible. Similar is the case here. That is for the portion that I am highlighting now. This is again, since y is less than normal flow, greater than critical flow, this again becomes zone 2 and any rising limb is not possible here. That would leave us only with one option. Let us see that whether this raise is possible. Now in this case, this is mild. We are at the point that I am highlighting right now. We clearly know that our depth of flow is greater than yn. That means we are in M1 zone. M1 zone has to be the case of backwater, or that means that in this case dy by dx can be greater than 0. That means this is possible, and as soon as it reaches the transition points, yn definitely is possible because this corresponds to normal depth. So out of all the three options, the profile that is now highlighted is the one that is possible. That is, this transition starts taking place little early, water rises a bit and then joins the normal depth of flow corresponding to milder channel. We can extend similar discussion to various combinations. Let us say that now we have exactly opposite scenario, that we have a milder slope followed by a mild slope, and this is some critical depth line here, CDL again. So this corresponds to the transition point at this kink or wherever there is change in slope. We say this as critical depth line. Also, for this milder slope, our normal depth of flow is going to be little higher. For mild slope, normal depth of flow is going to be little lower. Water is flowing in this part and now it wants to transit downstream on mild slope here. So we have to connect the dots, that how we should connect this region with the region downstream that we have shown. Now let us all look into again the possible transition paths. One way is that now I will be using red colors so to ensure that we are able to see the different profiles, that it takes this path and ultimately gradually comes at this level. This is possibility A. Possibility B is it starts reducing here and joins here. Possibility C is it goes down here and come back and join here. So I'm just drawing three possibilities, whatever comes to my mind. You can have any other possibility that you seem fit and try to see whether that is physically possible or no. If you look at choices A, B and C, now here this would correspond to zone 2 now, because this is zone 1. Anything above the normal depth of flow is zone 1. Between CDL and NDL we have zone 2, and this is zone 3, which is not coming into picture. In zone 2 we can definitely have a drawdown, so this case looks feasible. So when we up to this point, this is definitely feasible. But at this point, again, we are in zone 2, because for the mild slope that we have here, the point which I am showing by cross is again in zone 2, and in zone 2 we understand that water cannot rise back. So that would rule out the profile that is trying to go decrease up to that transition point and then increase. Similarly, if we talk about A, up to the point of transition there is no problem whatsoever, but the water depth here corresponds to M1, and M1 cannot be decreasing profile in gradually varying flow. That means this is also ruled out. So we are left with the third option to examine, that we are in zone 2, profile is declining, which makes sense, and ultimately it is joining normal depth of flow. That means B is the correct answer, that how this transition can take place. The most plausible explanation is B, or the transition would happen along the path B using the M2 profile and ultimately joining the normal depth of flow. Now, there can be multiple combinations, milder to mild, steeper to steep, steep to mild, mild to steep, and so on. But the rationale that we have presented in these two questions would remain more or less same, which we will also discuss during our in-class examples. Now, we have learned so many things about open channel flow, but the question remains how we can put all this information together to come up with the steps to design the channel. And specifically here, we would be talking about rigid bed channel, and same discussion can be extended to the flexible bed channel. But in that case, scouring conditions have to be taken into account very carefully. But for this particular introductory course, we will limit our discussion to rigid bed channels. But the concepts that we would learn here again would generalize. Now, before you start designing a channel, you would need some information which would be sort of required. Without that, there is no point in designing the channel. That means what is the discharge for which you are designing the channel? What is the slope of the bed? What is the material of which this channel would be made? And if this material is not given, you can assume that this could be a concrete line or a brick lining. But these are the three information that is definitely required. And finally, depending upon the country in which you are designing the channel, what are the codal or design standards that have to be followed? Now, in case of India, we have Bureau of Indian Standards, specifically IS 10430 and Central Water Commission guidelines give us some provisions that all the design, both for flexible as well as rigid bed channels, should adhere to certain standards, and we are going to touch upon those into some examples, which we will again cover into our in-class discussions. Now, what these guidelines are? These guidelines basically tell us that what is the maximum permissible velocity of flow, keeping into mind scouring or erosion. What is the minimum freeboard? That is, you will design channel for some depth y, and then we have to give some freeboard. How much that freeboard should be for different kinds of channel, that is what we have to look into. For different values of discharges, that is for different values of Q, what kind of shape we should have. So for example, if our depth of flow is very less, it is recommended that we should go with a triangular channel. If we are designing the channel sections, designing carrying Q, let us say greater than 50 meter cube per second, it is recommended that we should design a trapezoidal channel. And the slope of the sides, the width of our channel would ultimately determine the velocity, and we will keep on reiterating up our designs until our velocity of flow is within the permissible limits, both on higher sides as well as lower sides. Because if we give a section which is unable to even sustain minimum flow velocity, water will become stagnant, and that would have its own repercussions. On the other hand, if water becomes much faster, a lot of its contribution of energy would be coming from kinetic energy, and we have already learned that if maximum contribution is in form of kinetic energy, that water power becomes highly erodible, which we also don't want. Now, with this information, let us look into the steps that how we would proceed ahead. We learned that in case of uniform flow, our Q is equal to 1 by n, R to the power 2 by 3, S to the power 1 by 2a, and this is Manning's formula. If we bring all the geometrical terms on one side and keep the information giving on other side, for example, we can write this as a r to the power 2 by 3 into a, it should be equal to n into q divided by s to the power 1 by 2. Now, if we know that the channel bed properties, we should be able to know its roughness coefficient. We need to know discharge and of course slope, because that's what I mentioned, that this is the minimum information that you need before you start designing the channel. And this information about Q generally comes from our understanding of hydrographs, which we have already learned in the subject of hydrology or first part of this course. Now, based on this, we have determined R2 by 3A. Now, what we will do from here, we will assume some side slopes. And recommendation for these side slopes, depending upon what material we are using to construct our channel, are again given in table 2 of IS 10430, and depending upon the country, you would find the relevant standards applicable to your nation. Now, once we decide the side slope, we have already introduced some design curves where using these design curves, you should be able to compute that what is the variation of AR 2 by 3 with B naught as well as Y. And once you use these design curves, you should be able to come up with the Y. And this becomes a typical problem that we were solving in Manning's equation, where everything is known under certain conditions, and you do a back solving using our design curves and calculate this value of Y. And depending upon shape of the channel, so that design curve will have the variation of Y. So on x-axis we will have something like variation of AR 2 by 3, and what are the Y's for different cross sections, maybe for trapezoidal, for uh, rectangle, as well as for triangle. And depending upon what shape you are looking at, we will look at the corresponding design curve and should be able to calculate Y. Now, once we solve for Y, this is the total Y for which we are designing, and then we will also add a freeboard. Freeboard would ensure that if our depth of flow is 10 meter or 5 meter, let us say, and recommendation is there should be 20% of freeboard. So we will say that we will design this channel bed for 5 plus 0.2 times 5 meter of depth. But then what is one final step that is left? Once the entire cross-sectional properties are determined, that is, we know that width of flow, we know the depth of flow, what we will do, we will calculate the velocity and apply the final check that velocity should be less than the maximum permissible velocity, which again is guided by the codal provisions. And once we have this, our design is complete. So with that, we try to put all the concepts together that we have learned and ultimately come up with the engineering design of a channel section.